My name is Roy Levin. Today is August 12th, 2016, and I'm at the Computer History Museum in Mountain View, California, where I'll be interviewing Leslie Lamport for the ACM's Turing Award Winners Project. Morning, Leslie.
Good morning.
I want to start with the earliest time that you can remember being aware of computing.
Aware of computing. Probably in my junior year in high school. I think I came across a book that discussed Boolean algebra and must have discussed computer circuitry a little bit because I got interested in trying to build a computer. Didn't get very far, but I think it was my junior year in high school, possibly senior year.
So that would have been what year?
55, 56.
And you were not so much aware of the state of computing devices at that time, rather more the mathematics behind computing circuitry.
Well, I must have been aware of the existence of computers. I seem to recall they existed in the movies. Wasn't it The Day the Earth Stood Still? There was
Yes.
a computer? Or am I just making
There's
that
certainly
up?
a robot. How the robot worked was another matter.
Yes.
I think, yes. The first time computers were sort of burst upon the public visibility might have been the election in which they were used for the first time to make predictions. Was that 1960?
I don't know. There was a period of time, probably when I was an undergraduate and going through a large amount of graduate school, where I was unaware of television.
So let's in fact talk about what happened after you became aware of these things in high school. Did you explore computing through high school and into your undergraduate time?
Well, I tried to build a little computer, and this was while I was in high school, and I visited the IBM headquarters in New York, and they were very helpful to this little kid who wanted to build a computer, and they gave me a number of vacuum tubes. In those days, they would replace them on regular intervals, and so they were still good. And so I think I got to the point with a friend of building a 4-bit counter, and but that impressed the interviewers at when I applied to MIT, so that had a good effect. But my first serious exposure to computers came the summer after I graduated from high school. Through some kind of city program that I forget, I wound up having a summer job at Con Edison, the New York electric utility, and that's New York City, the electrical utility. And I was assigned to do some very boring stuff, but I learned that there was a computer there, and I went up to the computer center and managed to get myself transferred to a job running tapes on their computer system. For the younger generation, tapes used to be a storage medium for computers, and they would be read on these large tape drives, and they would also serve as input and output, and so you'd have to mount the input tape for a program, run the program, and then remove the output tape and give it to whoever wanted the results. So that was my job, mounting tapes, probably starting the programs and stuff like that. But in my spare time, and in the computer spare time, I learned to program it. And the first program I can remember writing computed E to something like 125 decimal digits. That number being that the computer I was running on, which was an IBM 705, had an accumulator of 125 or so digits. And so I was able to do that basically without having to do multi-word arithmetic.
So I guess it was natural that your first program involved an interesting mathematical entity, since your interest in mathematics, from I gather from your resume, goes back even further than your interest in computing.
Yes, I was. I guess in some sense, to the extent that an elementary school student could be a mathematician, I was a mathematician throughout my school years, even though the idea of actually being a mathematician as a profession never occurred to me until around my senior year in high school. But even so, it seemed like not a practical way of making a living, and so I started out being a physics major, and maybe in my first or second year I switched to math, although I'm not sure if the reason was that I really thought that mathematics was a career move, but at MIT in those days, mathematics was the only major that didn't require you to write an undergraduate thesis.
Practical, as always. So you actually were thinking at some level about careers coming out of high school and going into your undergraduate days, it sounds like?
Not in a very concrete sense, in terms of, I think if I become a physicist, I will be able to get a job doing thus and such. Although it was clear that becoming a mathematician, the only thing I knew that mathematicians did was teach math. So I suppose at the time I switched to a math major in college, my career goal would have been to be a professor of mathematics. And I should mention that throughout my studies, I had part-time and summer jobs programming. My undergraduate years at Con Edison, I went back to them for summers, this time as a programmer, and continued, and also worked part-time in the computer lab at MIT, and that was also running tapes. But as an undergraduate, I also remember doing working as a programmer for someone in the business school.
So programming and math and physics all were interwoven during your undergraduate days, but you thought of them as sort of separate activities in some way.
Well, they were interwoven temporally, but
Yes.
they were completely different worlds as far as I was concerned.
And when did you first notice or become aware that there might be some, let's call it science, related to computing, as distinct from it just being a technology for calculation or something?
That's a difficult question. I really can't answer that. There was some point in my career at which I suddenly realized that I was a computer scientist. But I can't say when. It probably happened before I went to SRI, which was in 1977. The first thing I published was a letter to communications of the ACM commenting on an algorithm that had been published. It was an algorithm for implementing a hash table, and I discovered some very slight improvement one could make. Then thinking about the problem, I realized that there was a simpler way to do the hashing, and started collecting data on efficiency or something or other. And when I was in the midst of doing that, someone published a paper in ACM with that method. And for quite a while, that was the standard method for implementing hash tables. But I had discovered, I think, 3 variants or techniques for implementing the idea that weren't mentioned in that paper. And I wrote a paper just describing those 3 methods. And it was returned by the editor saying it was just not interesting enough, be worth publishing. In later years, 2 of those methods, each was published in a separate paper in the ACM, but by a different editor. Just an amusing little historical footnote.
Well, you began to learn pretty early on how the vagaries of editing and review and publication work. That's a topic actually I want to come back to later, but I want to continue now with a more chronological view of things. So, while you were you mentioned SRI, but before you went to SRI, you were at Compass for some years. How did you come to be working there?
When I went back to graduate school to finish my degree, I needed to get a job to support myself, and somebody, actually a professor at Brandeis, where I was a graduate student, recommended I check with Compass, which official name was Massachusetts Computer Associates.
Yes.
And they gave me a job that, well, first was supporting me through the rest of my graduate studies. And when I got my degree, I was all set to take a teaching job at the University of Colorado in Colorado Springs. And Compass said, wait, would you like to keep working for us in the new California office we were going to set up? And I thought about it and decided, yeah, that sounded good. And so by the time I'd actually gotten around to being ready to go to California, they said, whoops, the California office has been delayed, but that's okay. You can go out to California and work for us, which I did. And I worked for them for another 5 years, I think. And they never did open a California office, but I kept working for them from California and would visit the home office outside of Boston for about a month once a year.
So that's very interesting, an early example of telework, which is, of course, these days a more common notion. What kind of work were you doing? Maybe it would be useful to talk a little bit about the kinds of projects that Compass did and what the business was.
Well, Compass's main business was building Fortran compilers, but they also had random contracts with the Defense Department for doing different things, and with some companies. One of the things I did was design a file system for a computer that was being built by Foxborough, and Compass had the contract for doing software for that new computer. I don't remember exactly what. That was, I suppose, would have been the first concurrent program I actually worked on, if the idea of concurrent programs was known. But instead, it was actually worked by using interrupts.
So I'm intrigued by the remote working arrangement that in those days, it seems to me, would have been quite a difficult way to develop software. Can you say more about how you actually did that?
Oh, I'm sorry. That Foxborough project was while I was still living in Massachusetts.
I see.
In the course of another contract that Compass had was building the Fortran compiler for the ILIAC 4 computer, which was an array computer, we call it today, with 64 processors, which was an enormous number in those days. And I worked on the problem of compiling sequential Fortran code into code for parallel computer. In particular, parallelizing Fortran do loops. And I developed, I guess an algorithm, or I would say perhaps even more so developed the theory behind it, which in terms of theory was pretty simple. It was basically integer linear algebra. At the time, I had a friend who had some land in New Mexico that we would take a week or two vacation and stay with him. And what I proposed to Compass was that I'd go spend, I forget whether it was 1 or 2 months there, working on this problem. And I said, okay. I did that, and while I was there, I wrote a tome, I guess you'd call it a paper, although it was handwritten, maybe about this thick in sheets, and presented it to them. And this, I think, blew their minds, the notion of using linear algebra. And I learned later from observation that this tome that I delivered, it was like Moses delivering the stone tablets. It was practically a sacred text that people studied, and they did use it to build the compiler. But what it did serve is to reassure the people at Compass that I could go off by myself without supervision and actually do something useful. So they sent me off to California. And I don't remember what my actual assignments were, if I even had any, but I was being paid on some government contract. And it was, I think, about 6 months after I moved to California that I developed the bakery algorithm. And I think from that point, it became clear to Compass that I was a researcher that they were going to support. And my memory is that I was left pretty much to myself to figure out what I was going to do, and they would find contracts to support me.
So the bakery algorithm is obviously a very important milestone in your career, and I want to talk about it quite a bit later. But for the moment, I want to pursue this notion that Compass was, even though they didn't really formally have a research organization, certainly not in California, they were in effect supporting you as a researcher. Is that right?
To the best of my memory, yes.
Okay. So it seems like it was a fairly open-minded research environment, if you want to call it that, at least as far as your interests were concerned.
Well, I think from Compass's point of view, they were happy to work for anyone who would pay them, and they figured out that the Defense Department would pay them to have me do research, and so that's what they did.
So the bakery algorithm, you invented that. We're talking early 70s now, right?
Yes.
And it got published, if I remember, in 74. Is that correct? Something like that.
That sounds about right.
Yes. So Compass was also comfortable with the notion of independent publication in those times, that you could go off and do this publication presumably on your own. Is that okay?
Oh, sure. This notion of intellectual property didn't really exist as a practical sense in the computer industry, at least in terms of any kind of research in those days. I think that it was probably even before the days of software patents. I'm not sure of that. Certainly it would have been before the days of patenting an algorithm. And so, no, there was no notion that anything would be, not published. And of course, anything that was published was effectively serving as advertisement for Compass, so they were quite happy with that.
In fact, wasn't in those times that algorithms more or less routinely got published in the communications of the ACM as sort of people throwing out, here's my algorithm.
There was an algorithm section in CACM. That's not where I published, because those algorithms, they weren't algorithms. They were, there was probably somewhere between algorithms and code, because you had to submit a working program. And how could I submit a working program on the bakery algorithm when multiprocessor computers essentially didn't exist?
So let's talk a little bit more about the bakery algorithm at this point. Can you tell us a little bit about how you came to be interested in the problem?
Oh, I can tell you exactly. In 1972, I became a member of the CACM. And I think one of the first, of the ACM, and one of the first CACM issues that I received contained a mutual exclusion algorithm. And I looked at that, and it seemed to me that that was awfully complicated. There should be a really simpler solution. And I decided, here's a very simple solution for two processors. I wrote it up, I sent it to ACM, and the editor sent it back saying, here is the bug in your algorithm. That taught me something. It taught me that concurrency was a difficult problem, and that it was essential to have proofs of correctness of any algorithm that I wrote. And of course, it got me mad at myself for being such an idiot, and determined to solve the problem. And in attempting to solve it, I came up with the bakery algorithm. And of course, I wrote a careful proof, or for those days was a careful proof. And in the course of writing the proof, I discovered that the bakery algorithm had this amazing property that it did not require atomicity of reads and writes. And I understood that was a really cool thing, and I'm not sure at which point it made me realize that I had really solved the mutual exclusion problem, because I had written an algorithm that didn't require any underlying mutual exclusion, something that there was one article by Per Brink-Hansen that said was impossible. So felt nice having solved an impossible problem.
So you wrote up the algorithm and submitted it with a proof.
Yes.
Do you recall how the editor of the journal reacted at that point? Was it a straightforward, oh great, I'll accept it, or something more complex?
It was straightforward. I mean, he sent it out to referees. The referees, I don't remember any significant comments from the referees, and it was published without a problem.
So this was a piece of work you were doing while you were employed at Compass. Did you share it with colleagues there?
I did. In fact, the next time I was out at Compass, I showed it to a colleague, Anatol Holt, and I got the reaction I don't think I've ever gotten from anyone else, which told me that Tali appreciated that algorithm more than anyone else had. Because when I showed him the algorithm, he said that couldn't be right. And I showed him the proof, and he listened to the proof, he went over it, he said, well, I don't see any hole in this algorithm, but it must be wrong, and I'm gonna go home and think about it. And I'm sure he went home and thought about it, and of course, never found anything wrong with it. But I was very impressed by this visceral approach that Tali took to the issue. Tali, by the way, was he was an I don't know if you call him an advocate, but a believer in patronets, and he was also interested in, I would guess we would now say was fundamental issues in concurrency. And every year for about 3 years, I would go back to Compass, and Tali would have his new theory of concurrency, and he would give some lectures on it. And it would start off, in some completely different way, but then it would always wind up at patronets. And it was all very lovely, carefully reasoned, but it just struck me as being not very useful, because I realized that patronets had nothing to tell me about the bakery algorithm.
Was that a conversation that you had with him about your study of the bakery algorithm and the fact that his methodology for talking about concurrency didn't work with it?
No, I don't think we ever had a discussion about that. I learned some, I think, important basic things from Tali, and I'm not sure what they were, but I think the experience of thinking about things in terms of patronets was in fact useful. Tali is probably best known for as being one of the inventors of marked graphs, which are a particular class of patronets that are quite interesting. They have have very nice, very simple properties, and in fact are a useful model of a lot of real-world computation. It just they weren't going to be useful to me in general, as a general way of looking at concurrency.
Coming back to the bakery algorithm itself, I've read in one of your perspectives on it, that you thought it was the one algorithm that you discovered rather than invented. I'm not sure I understand the distinction. Can you elaborate on that?
I'm not sure I understand the distinction either, but there just seemed to be something fundamental about it. And maybe the basic idea of the use of a counter, a sequence of numbers that can, in fact, increase forever, that you will see elsewhere in things I've done, in the time clocks paper, for example, the use of timestamps or that kind of counter. And in the whole state machine approach and Paxos, there's, well, in Paxos, there is also a counter that's being used in, not quite in the same way, but it seems like there's some fundamental thing going on there, and I don't know what it is exactly, but it's certainly been quite useful to me.
Well, all those algorithms that you mentioned are things that we'll talk about some more, because I think that's been a very significant thread in your work, starting with the bakery algorithm. You've also said it was the one you were proudest of. Can you say why?
No, I can't.
Well, that doesn't need to have a rational basis, I suppose. So that happened while you were in sort of independent researcher mode. Yes, go ahead.
Let me try to answer the question of why I'm proudest of it. I think in other things that I've done, I can look back and see this idea developed from something else. Sometimes leading back to a previous idea of mine, very often leading to something somebody else had done. But the bakery algorithm, it just seemed to come out of thin air to me. There was nothing like it that preceded it. So perhaps that's why I'm proudest of it.
Well, certainly mutual exclusion is an absolutely foundational problem in concurrency, and to have solved it, as you did in the bakery algorithm, certainly something worthy of being proud of. As part of the publication of the bakery algorithm, you included the proof that you talked about. Was it common for papers around that time in the early 70s to include proofs with algorithms that were published?
I don't know about algorithms in general, but mutual exclusion algorithms, which are pretty much the only concurrent algorithms that were published in those early days, approximately, but it's the most significant concurrent programming problem. And yes, Dijkstra's first paper had a proof. And it was interesting, the second paper, which I believe was a note submitted to ACM, didn't have a proof. Knuth then published the third algorithm, pointing out the fact that the second one was incorrect. And I'm sure he had a proof as well. And yeah, the mutual exclusion algorithms always contained a proof.
So for concurrency, at least in those days, that was the norm, even if it wasn't the norm perhaps for other kinds of algorithms.
Right.
Okay. And your work evolved from the bakery algorithm quite a bit, but was often driven by what you had learned in studying it. And in fact, the future study of that algorithm, I think you've written, was something you did for a number of years. Did that study lead you into the approaches for verifying correctness that you eventually spent quite a bit of work on?
My interest in correctness was parallel to my interest in concurrent algorithms. I should mention, I don't want to make this, I don't want to give the impression that I was drawn to concurrency by these fundamental problems. The fact of the matter is that they were just really cool puzzles. And when I was at Con Edison, I had someone who took a manager who became sort of a mentor to me. And he would give me his problems. And one problem he posed to me was, in those days, programs were on punch cards. And you would load the punch cards into the hopper, and you'd press a button on the console, and the computer would read the first card, and then put that card in memory and execute that piece of memory as a program. So the first card would usually be something that had just enough of a program in it to load the rest of a few more cards, so you'd have a decent-sized program that you would then execute to load the program and start that program executing. Well, I remember he posed the problem to me to write a loader that worked all on a single card. And I worked on that problem, and I would present him with the solution, and he'd say, "Yeah, that's good. Now make your loader also have this property," and went through a few iterations like that. And I was I just loved those puzzles. I mean, one thing I'm also proud of is a program I wrote for the IBM 705, which was when your program crashed, you would take a memory dump and also presumably print out as much as you can of the registers to try to find out what went wrong. And of course, starting that debugging process meant putting a punch card into the hopper. And so the problem I faced was, well, if you do that, well, it's going to erase part of what's there. And executing the program is going to erase some of the registers that you want whose contents you want to print out. So, how can you do that? And there was one register whose only function was as a destination for a move operation. That is, you say move something, and you move a piece of data from some location to the location specified by that register. So the problem was, how do you read out that register? Because it could put, you could put something in the register. You could go anywhere in memory, so you have to look through all of memory. But it could also land on top of the program that you were trying to to find it. So I figured out how to write a program that even if the transmit to the move instruction put this piece of data right anywhere inside your program, it would still work. And I still think that was a really neat solution.
What did your boss at Con Edison think?
I don't remember if I must have showed it to somebody, but I don't remember the reaction.
So I was wondering if they actually ended up using it. You could take credit for writing a debugger.
Oh, no, I don't think anyone cared that much about that register to worry about it. But the thing about concurrency is that it added a whole new dimension of complexity. And so even the simplest problem became complicated. It's very much like just as trying to write a program where, something could transmit a value into the middle of your program, where you're trying, in concurrency, you're trying to write, get a process to be able to do something, even though another process could be doing anything else that that process might do. So it posed that same kind of difficult puzzle, and that's what attracted me to concurrency more than a desire for fundamental theory. Once I started working on concurrency, then I became interested in what I might call fundamental problems in concurrency. But initially, it was just fun puzzles.
Very interesting. That's great. So let's continue the sort of chronological thread a little bit. You worked at Compass until 77, is that right?
Yes.
When you moved to SRI?
Right.
How did that come about?
Oh, for some reason that I never understood. The people at Compass said that it was a nuisance having me in California, and that they said I had to move back to Massachusetts. And I didn't want to move back to Massachusetts, so I found a job in the Bay Area.
Mm-hmm. And how did you happen on SRI?
I knew people at SRI. I think SRI and Xerox PARC were the only places I knew that did computer science research. And I applied both places, and PARC didn't make me an offer, and SRI did.
And what was SRI's business in around that time? What kinds of things were going on there?
Well, SRI was very much like Compass in the sense that you find somebody to pay for it, you can do it. Mm-hmm. But the major project the obvious project for me to work on, and I suppose they had it in mind when they hired me, was the SIFT project, which was to build a fault-tolerant computer system to fly airplanes, essentially. It was a NASA contract. And that was the contract that led to the Byzantine general's work. So that's what I started working on.
Let's talk about SIFT a little bit more. So that was already underway when you joined SRI. And it seems like in the late 70s, if we sort of think back to the state of aviation in those times, the notion of having computers flying an aircraft was pretty audacious. Do you know how it was that contract came about?
Well, I don't think it was such an audacious idea. And the motivation for it, as I understood, was not long after the oil crisis of the early 70s, where because of an embargo or some kind of embargo, it's not clear exactly what was permitted and what in fact wasn't. There was an oil shortage in the U.S. and lines at gas stations, and that didn't last for very long, but it made made people think about trying to save gasoline. And the one way that they were able to save gasoline or jet fuel was designing airplanes. Designing an airplane, you want to minimize the friction. And a large source of friction are the stabilizers, the horizontal and vertical stabilizers that control the plane and keep it flying straight. And they realized they could cut down friction and save fuel by reducing the sizes of those control surfaces. But doing so would make the plane aerodynamically unstable and unflyable by a human being. And so only a computer would be able to fly it, because you'd had to basically make corrections to the control surface on every few milliseconds. And if you didn't, you could get vibrations and the wings would fall off. So I think another motivation was, another thing that reducing those size of the control surfaces did was make the plane really maneuverable. So you could build fighter jets that could really maneuver, do tight turns and all that stuff, but if you could get computers to fly them. So I think those were the NASA's two motivations.
Mm-hmm. And the project was underway, as you've said, when you joined. What was your role in that project when you joined it?
Well, my general role was a member of the team, engaging with the conversations and lots of decisions and stuff. But perhaps the question you're asking is which of the results that are still known under the aegis of the Byzantine generals' work did I contribute to, and which were there when I arrived. And the idea of what was there was the notion of the problem, namely achieving consensus in the face of completely unreliable processors. And the solution that did not employ digital signatures was known. The solution and also the impossibility of the result that you couldn't do it with 3 processors, you needed 4. And the algorithm for 4 processors, I believe, was invented by Rob Shostak before I arrived. And the generalization to 3n+1 processors was done by Marshall Pease. And that was an amazing piece of work of Pease. I don't know how he figured out that algorithm. Nobody could understand it. I mean, I could read the proof and follow the proof, and was convinced that it was correct, but I still couldn't say that I understood it. And what I contributed to the original paper was the algorithm with digital signatures, which was actually something that I had done before I got to Compass. Before I got to Compass, I wrote a paper, and I think it was published in '77, and nobody noticed it, which actually generalized the time clocks paper to the problem of implementing a state machine in the presence of arbitrary failures. And since in those days it wasn't clear what you consider as a failure, I just considered arbitrary failures. That is, where a failed process. These days, most work on failures assumes that processes failed by crashing, but it wasn't clearly the right model or the useful model in those days. So I had an algorithm that would tolerate arbitrary failures, including processors that acted maliciously. And I didn't discover the impossibility result because it doesn't apply if you have digital signatures. Digital signatures, you just need a majority of processors to be working correctly. The other thing that I hadn't done is to pull out the consensus problem. Now, it's clear that if you're trying to build a system that works that works correctly, you have to choose a sequence of operations that should do. And so you have to form consensus on choosing each of those commands. And I hadn't pulled out the consensus problem as something to be considered separately, as a building block. And I'm not sure why, but I think in retrospect, it's because the solution to that problem, the one using digital signatures, came so quickly to me that I didn't think much about it. And the reason the digital signature algorithm came from me is, in those days, hardly anybody even knew about digital signatures. I happened to be a friend of Whitfield Diffie, and who, of course, with Marty Hellman, published in around 1976 the seminal paper that New Directions in Cryptography that introduced public key encryption and started the whole modern field of cryptography. At any rate, it was, I think, around 74 that I was having coffee at a coffee house with Whit, and he proposed the problem to me, which he hadn't, he realized it was an important problem, he didn't know how to solve it, and I said, oh, that doesn't sound very difficult. And I thought a minute, and literally on a napkin, I wrote out a solution involving one-way functions. And that was the first solution. Whit and Marty published it in their paper, crediting me, of course. So I was one of the few people in the world who knew about the digital signature problem and knew that it was possible to create digital signatures. Although in the context of fault tolerance, creating digital signatures should be trivial because you're only worried about a signature being forged as a result of a random failure, not as a result of a malicious processor. So it should be fairly easy to devise some algorithm that would guarantee that the probability of a forged signature is infinitesimal. Although I've never had occasion to really think very long and hard about that problem, and I don't think anybody else has either. So it's in some sense an unsolved problem of creating an algorithm that you can prove in the absence of a malicious failure has a suitably low probability of being broken by a random failure. At any rate, so that was the situation when I got to SRI. That original paper I contributed the digital signature algorithm. And perhaps the other important thing that I did was that I got them to write the paper, because I realized that this was an important result, an important problem. And publication, especially outside of academia, didn't seem to have as high a priority as a member of Xerox PARC. You may remember that it was there's a lot of great research being done, but not very much publication, and it was known as the black hole of computer science. Anyway, I sat down and I wrote a a paper on it. And I remember Rob Shostak not liking the way I wrote the paper at all, and so he sat down and rewrote it. And I imagine that something would have gotten published eventually, but I think it certainly got published sooner because I spurred them into action. And in the second paper, the only really new result in there was an understandable version of the general algorithm without digital signatures, a recursive version, and that was, I think that was one that I discovered. But the real contribution of the second paper was introducing the name Byzantine generals.
Which is what it's, of course, become known as ever since. Mm-hmm. Just to wrap up on SIFT.
By the way, you should ask me about the origin of the name at some point.
I will.
Okay.
Yeah. Just to wrap up on SIFT, how did that project conclude? Did the system get built? Did it get deployed?
A prototype system was built. I think it was run on a simulator. I'm not sure if it ever flew in an airplane. There was a bit of controversy at the end of the project. The project was to included a complete verification of the code. And there was some controversy about that. And the short story is that through carelessness, the paper that was published about it did not make it perfectly clear what had been verified, mechanically, had been mechanically proved, and what hadn't. I think in the particular case that the code that had been verified didn't include some optimization that was later made. So the final system included code that had not been mechanically verified. And there was this general sense in the criticism of it that this was this multi-million-dollar project, and they lied about that worked with that time, and they lied about what they had done. And the fact of the matter was that this project was used somewhat as a cash cow at SRI in our group, and the actual writing of the actual proof of the code was an onerous task that nobody wanted to do. And I managed to get off the project, before it became my turn to do that. And finally, Rob Shostak, it was Michael Melior-Smith and Rob Shostak in really a Herculean effort as the deadline was approaching, wrote the proof and ran it through the prover. And it was really, I would say, a baling wire and chewing gum type of project as far as this proof was concerned, rather than this, grand effort. And I think that although the people were careless in what they published, this was not a serious offense, and I think the project was quite successful.
And do you know if it had any direct impact on the way avionics systems were subsequently designed?
Well, I don't know how avionics systems are designed. The Byzantine generals' work certainly did. I was actually curious about that, and sometime maybe 15 years afterwards or so, I happened to be contacted by someone who had been at Boeing and asked them if they knew about the Byzantine general's work. And he said, yes, indeed. He said he had been the one who first read our paper, and he said, oh shit, we need 4. Though he did say that this was in the commercial side, and he did say that Boeing had just bought McDonnell Douglas, I believe, who were doing the military aviation side, and that he, from what he said at that time, the people in McDonnell Douglas were somewhat clueless about these things. I don't know what goes on these days at Boeing. I have no idea what goes on at Airbus. I happened to visit Airbus and was told that they use a primary backup system rather than the SIFT type design, which was, I guess, what you call peer-to-peer these days. And basically the programmers, that was in the job of the hardware people. That was done in hardware. And you can build a primary backup system correctly, handling Byzantine faults. On the other hand, I've seen occasion where engineers have very happily presented solutions of provably unsolvable problems. So I don't know, so I'm not positive that the engineers who build the Airbus know about the Byzantine general's results. So, but Airbus is very secretive about what they do, and you or I can't find out.
And you don't let it affect your flying habits.
One thing that I have observed is that, well, let me give you one little anecdote. As you remember, at Digital Circ Lab, where we were, there was a reliable distributed file system that was built called Echo. And that actually motivated me to discover Paxos, because I was convinced that what they were trying to do was impossible and was trying to find an impossibility proof, and instead I found an algorithm. But there was no algorithm behind that code. There was just a bunch of code. And I'm sure that there was kind of failure that Paxos would handle that the Echo code didn't handle. Mm-hmm. But the Echo system ran perfectly reliably for how many years? I don't know, 5 years or something like that. And it only crashed once. And the reason for that crash had nothing to do with the algorithms. It had to do with a very low-level programming detail that buffers got overfull. And so whether or not the Airbus engineers will handle all possible Byzantine faults, I think that in practice, if they're probably good engineers, and they've probably thought about the problem enough that if there are failure modes that would cause their algorithm to fail, they are sufficiently improbable that they're not the most likely cause of an airplane crash.
So you were at SRI for 7 or 8 years, and then you moved from an organization that was fundamentally a contract programming or contract project organization into what I think we might call a corporate research lab at Digital Equipment Corporation. How did that move come about?
Oh, well, the actual details is that we were in a group that had, I don't know, a dozen people or so. And at some point, they decided that we needed another level of management. And that, in addition to the lab director and assistant director, there was now, 4 of these 12 people became, some managerial title and something. And I just said that was ridiculous. And Bob Taylor had just started the Circ lab, and it was a natural place for me to go.
So you came into must have been a fairly small group of researchers at that time, since the lab was just getting started.
It didn't strike me as being small because it was probably larger than the group at SRI where I was. So,
But there wasn't a single project you were basically being brought into as you had been at SRI.
no, it was clear that I was being brought in to become a member of the lab. There was much more of a sense of community at Circ than there was at SRI, which may seem strange because at Circ was a much larger place. But as someone said at SRI, that grant proposals are our most important project. I'm sorry, grant proposals are our most important product. And so there was always this question of you were working on a project, and there was no sense of interaction between projects. So in a sense, the lab was more splintered than it was at Circ, especially in the beginning, where there was one project which was building the computing environment. So it was clear that my expectation was that I would be continuing the same line of research I'd been doing, but also interacting with the other people in the lab, because they were building a concurrent system, and so they would have concurrency problems, and so I expected to be useful.
So how would you characterize the most important product of Circ by analogy with what SRI said? It clearly wasn't grant proposals.
I think, I'm getting out of my depth because this is a question of, why did digital open the Circ Research Lab, and what did digital expect to get out of it? Of course, as you know, the kernel of the people who started Circ were the people who came from Xerox PARC, where they had just created personal computing. And so there was very much a sense that, this was what the lab was going to continue doing, creating the computing of the future. And so that was the purpose of the lab.
And so there was a qualitative feel to that organization that was different from SRI, is that right?
Definitely, but that, I think, had a lot to do with Bob Taylor, the lab director and lab founder, who was just a wonderful manager. And as you know, he was your mentor.
Indeed. Did you consider, when you were looking to leave SRI, other places to go work, perhaps academia?
I did talk to Berkeley and Stanford, but I must say I was never really serious about it. I did not see myself as an academic. So it was clear to me that CERC was where I was going to go if it made me an offer.
And say a little bit more about that. What is it about either the difference between CERC and academia that attracted you to CERC more than the university?
Well, there were two things at play. First, one was personal and one was institutional, you might say. Personally, I had never taken computer science seriously as an academic discipline. And in fact, when I started out, it wasn't. I don't think there was enough stuff that you could call computer science. It's certainly not in my field that merited being taught at a university. And this may be just my own background, which since I had studied math and physics, and perhaps if I had gone to an engineering, been an engineering major at MIT, I would have had a very different perspective, and I would have considered programming to be a perfectly fine academic discipline, but it never seemed to me that people ought to be going to a university to learn how to program. And by the time I began to feel that, well, maybe I actually could go to a university and teach academically respectable things to people, I was too set in my ways, and I think that maybe would have been in the 90s or so. So that was one reason why universities didn't interest me. And the other thing is that I found industry to be the best source of problems. And I think in the early days of concurrency, the early days starting in the late 70s, and going, it was in the late 70s and early 80s that we were talking about, a lot of academic research was just self-stimulated. People, especially theoreticians, contemplating their navel and deciding what should happen. And I've always found that the real problems, the important problems, were motivated by people in industry having things they wanted to do. I mean, SIFT was an example of that. I mean, it wasn't sponsored by an industry, but it was very much a real-world project. I mentioned Paxos, which was inspired by a real system being built at CERC. Bakery algorithm, not an industrial problem, but it was clearly important in programming. And what other ones? Oh, disk Paxos, for example, another algorithm happened because it was an engineer, a DEC engineer in Colorado, who said he wanted to build a system where instead of having to have 3 processors, he wanted to have 3 disks instead to get the redundancy. And that led to disk Paxos. Fast Paxos, no, sorry, not Fast Paxos, Fast Mutual Exclusion came because the people at World, the Western Research Lab, it was another DEC lab, but the people there were building a computer, and they needed a mutual exclusion algorithm that had certain properties. So, yeah, I've just always found not industry to be the best source of problems. Not all problems, but sometimes I suppose the most successful problems are ones where you think of the problems before industry realizes they have them, but it's certainly my experience working with industry, and even before that of programming, has been much more useful than most of what I learned in school.
So since 85, was it, that you joined CERC approximately? Until the present day, you've been in research labs, first at DEC and Compaq and now at Microsoft.
Right.
And that interaction of real-world problems and research and investigation has continued through that, essentially this whole portion of your career. Is that fair to say?
Yes. It's sort of an irony and a failure that although I look for real-world applications or real-world problems, I didn't interact with the people at CERC that much. And I think that I must have a prickly exterior that didn't encourage people to come to me with the problems they were doing, and I wasn't active enough in going out and finding people's problems because I always had things of my own that I was working on, and it was always easier to stay in my office and keep working on those than try to go out and talk to people and extracting their problems from them. So it more often would come from somebody outside the lab who had, knew about me or knew about my work and came with a problem.
So you've had a lot of external collaboration around problems and their solutions with people in academia, even though you didn't want to be an academic yourself. So there are evidently at least some people in academia that want to attack real-world problems.
I don't feel like I've collaborated with that many people. I think certainly compared to most computer scientists, I think I have more single author papers. Collaborated quite a bit with Fred Schneider, and I guess that's because Fred has, I think, a very similar sense of practicality that I do. Collaborated on a couple of papers with Ellie Gaffney. They both happened while Ellie was visiting CERC, and well, one of them was the disk Paxos problem, which I said came externally. The other one was on the mailbox problem, and that was a problem that I had myself, or a problem that had occurred to me many years earlier, and just Ellie's being there was an opportunity for it. There was the collaboration with the people at SIFT, at SRI doing SIFT. So that was, in some sense, the one time where I was really part of a group that I was actively collaborating on doing research.
Mm-hmm. So I'd like to shift gears now, and we've done a kind of a somewhat meandering exploration of your career chronologically, or at least part of it. But I think I'd like to start talking about some of the themes that have run through your career, and we've touched on a few of them briefly, but I would like to get into more detail on that. And the natural one to start with is probably the one that you worked on earliest, which we talked about a bit, the bakery algorithm and concurrency algorithms. You've said that quite a bit of the work you did grew out of the bakery algorithm and studying it, learning from it. One of those was, well, let me ask you this way. Probably the next famous paper that you produced was the time clocks and the ordering of events in distributed system paper, which is perhaps the one that's most widely cited. Did that grow out of the bakery algorithm study?
Not directly. It had a very specific origin. Namely, I received, this was while I was working at Compass, and from some connection, I don't remember why, but I received a technical report written by Bob Thomas and Paul Johnson, which was about replicated databases. And they had an algorithm in there. And when I looked at the algorithm, I realized that it wasn't quite right. And the reason it wasn't quite right was that it permitted systems to do things that in ways that seemed to violate causality. That is, things that happened before, one thing that happened before something else would wind up influencing the system as if they had happened in the opposite order. Now, the reason I realized that has to do with my background. And from my interest in physics, I happen to have a very visceral understanding of special relativity. In particular, the four-dimensional space-time view of special relativity that was developed by Minkowski in the famous 1908 paper. And I realized that the problems in distributed systems are very much analogous to what's going on in physics, because in relativity, because in relativity, there's no notion of a total ordering of events, because events will, to different observers, will appear to happen in different order. But there is a notion of causality, of ordering between two events, in which one event precedes another. If for every observer, it will appear that that event preceded the other. And the basic definition is one in which that is that if an event happens, where to some person, and the other event happens to another person, then it's possible for a message or a light wave to be sent from the first person when that event happens, and that it will arrive at the second person before that second event happens. And I realized that there's obvious analog of that in distributed systems, which says that one event happens to one processor before it happened to another processor. If there was a message or a chain of messages that began at the first processor after this event and reached the second processor before his event. And that's and it's that notion of causality or before that was being violated in this algorithm. And I made a fairly simple modification to the algorithm to correct that. And that's the algorithm that was presented in that paper, along with the definition of the partial ordering relation. Now, I should mention that I'm often, one of the things that the algorithm used and that the Johnson and Thomas algorithm used was attaching timestamps to messages. That is, each process has its local clock, and it timestamped a message with the time on that clock before sending it. And people have credited me with my inventing timestamps, which I didn't because I got them from the Johnson and Thomas paper. And what I didn't recognize at the time, when I received that paper, I just assumed that timestamps were a standard technique that people used in distributed computing. This is the first time I'd even thought about the problem of processors communicating by sending messages. And so, I didn't point out that timestamps were used in the Johnson and Thomas paper, and so their paper has been forgotten, and it remains as a citation, one of the 4 citations in my Time Clocks paper. One of the others being the Minkowski paper, and another one being a previous Einstein paper. At any rate, that's just a footnote. The other thing I realized that I believe Johnson and Thomas didn't realize is that this algorithm was applicable not just to distributed databases, but to anything. And the way to express anything is a state machine. What I introduced in this paper was the notion of describing a system by a state machine. Now, a state machine is something that's really simple. It's something that's started in an initial state, and it then takes steps which change its state, and what it can do next can depend on incoming messages, in this case, or from the environment, or it can come from the current state of the machine determines what it can do next. Now, the ideas of state machines, of finite state machines, are ancient, dating to the 50s or so, but they were all used as finite states, namely that the state had to be a fixed, bounded set, like a certain collection of registers or something. And it was very clear to me and to everybody that finite state machines were not terribly interesting as ways of talking about computation or about problems. But if you remove the restriction about them being finite, then they're completely general. And you can describe what any system is supposed to do as a state machine. And what I realized, and said in that paper, that any system, if it is a single system, in a sense, what it's supposed to do can be described as a state machine, and you can implement any state machine with this algorithm, so you can solve any problem. And as the simplest example I could think of, I used a distributed mutual exclusion algorithm. And since distributed computing was a very new idea, this was the first distributed mutual exclusion algorithm, but I never took that as seriously as an algorithm. And nor do I take the Time Clocks paper's algorithm as necessarily the solution to all problems, because although whether in principle you can solve any problem this way, that is building a system not without failures. It didn't deal with failures. It's not clear that the solution would be efficient, and there could be better solutions. And in fact, I never thought that my distributed mutual algorithm would, in any sense, be an efficient way of doing mutual exclusion. Well, the result of publishing the paper was that some people thought that it was about the partial ordering of the events. Some people thought it was about distributed mutual exclusion. And almost nobody thought it was about state machines. And as a matter of fact, on 2 separate occasions, when I was discussing that paper with somebody, and I said, really the important thing was state machines, they said to me, "There's nothing about state machines in that paper." And I had to go back and look at the paper to convince myself that I wasn't going crazy, and really did mention state machines in that paper. I think over the years, the state machine concept, thanks in part to Fred Schneider talking about state machines, people have gotten the idea. The way I met Fred Schneider is he sent me a paper. I don't remember what it was about that he had written. He was still, I think he may have been a grad student or possibly, I think he was a young faculty member. And I sent him, excuse me. He was working somehow along similar lines, and so I sent him a preprint of the time clocks paper, which I think subsumed what he had been doing. But I thought, this guy's pretty good. I should stay in touch with him. And I was right.
So this paper has been very widely cited. Obviously, because you did a foundational thing, and whether people really understood that or not, somehow they decided it was the place to point to in their own papers. Do people continue to, this paper was a long time ago, almost 40 years now, since it appeared. Do people continue to discover the paper and learn things from it?
Well, what amazed me is that I recently learned that there are physicists, or at least one physicist, who takes the paper very seriously and says it's very important in developing a theory of the physics of time. And now, this boggled my mind. I could understand, I regard what I did in that paper, at least this partial ordering that I defined, as being very obvious to me, because I understood special relativity. And so I figured, well, it seems really magical to most computer scientists because they don't know any special relativity. But of course, the physicists understand special relativity, and they thought it was a seminal paper. And so I got me thinking why, and I finally figured out for the physicists, and I confirmed with one, that what my paper did, the advance that my paper made, was that Minkowski was talking about, in some sense, messages that could be sent to define his relation. And I changed that to messages that actually were sent. And this seemed to me to be perfectly obvious, but to the physicist, this was a seminal idea. So it seems that things that seem obvious to me do not seem obvious to other people. I've never understood quite why the paper is considered so important in computer science, because the algorithm that it presents is of no particular interest. It has historical significance, but I think that somehow what people get out of it is a way of thinking about distributed systems that was so natural to me that I considered it obvious, that is not obvious to them and gets them to be thinking in a different way. This may be related to one difference between me and I think almost all researchers in concurrency, certainly theoreticians, is that in most of the research that most of the papers that people write or people I talk to, they think of something like mutual exclusion, for example, either as a programming problem or as a mathematical problem. I think of it as a physics problem. The mutual exclusion problem is the problem of getting two people not to be doing something at the same time. At the same time, that's physics. And I look at things from a very physical perspective, and which I think gets me looking at the essence of problems and not getting confused by language the way a lot of people do. I've observed something in computer scientists that I call the Whorfian syndrome. The Whorfian hypothesis, Whorf was a linguist early in the 20th century, his hypothesis is that the language we speak influences the way we talk. Well, what I call the Whorfian syndrome is the confusion of language and reality. And people tend to invent a language, and they think that that language is reality. And for example, if something can't be expressed in the language, then it doesn't exist. Let me give you an example. I've talked about state machines. Well, you can model a program as a state machine. And if you model it mathematically, basically what you're doing is mathematical description of a state machine. And so the state machine has to consist of the complete state of the system. Now, if you consider a program, part of the state of that state machine describing the program is what I call the program counter. It's the thing that tells you where in the program you're executing, which statement you're executing next. Well, there's no way of talking about the program counter in most modern programming languages. And so to people who are hung up in programming languages, the program counter doesn't exist. And so there are cases when, in order to reason about programs, particularly concurrent programs, you have to talk about the program counter. And I've talked to people who say that, well, at least one theoretician who works in programming languages said, that's wrong. You simply shouldn't say it. Wrong, what was the notion, the programming language jargon for wrong is not fully abstract. But he was saying that, my method of reasoning about programs, which involved the program counter, which basically you have to use, must be wrong. And other people have created methods that, since you have to talk about the program counter, they have ways of getting around it by introducing other things that can act as proxies for the program counter. So that's just an example of what I mean by the Whorfian syndrome. And I think there are a lot of people who are, over the years, have worked on problems that were meaningless outside of the context of the language in which they've been talking about them. And that has not been my problem. I believe, I may suffer from, the Whorfian hypothesis may apply to me equally well, but I don't get hung up in the language I'm talking about. Look at the physical reality that underlies these things. And it's that way in concurrency problems. I think the reason why things that I've done have turned out to be significant years later is not that I have any more foresight than anybody else or no better way than anybody else of predicting what's going to happen in the future. It's the fact that if I've dealt with real problems that have a real physical sense, that are independent of a particular language in which I'm talking about them, and it's those problems have a good chance of turning out to be useful. Whereas problems that are just an artifact of the language you're talking about are not going to seem very interesting when people stop using that language.
That reminds me of another paper that you did about the same time, not in the same thread as the time clocks or the Bakery algorithm, but about a problem that was very real at the time, the glitch, where there it seems a very physical thing enabled you to bring some insight to that others that eluded others. Could you talk about that a little bit?
Sure. Let me explain the glitch, which is more formally known as the arbiter problem. Imagine that you're, it's described in some paper by some housewife in those days. Housewife was not politically incorrect. And the milkman comes to the front door, and the postman comes to the back door, and they both knock at about the same time. And you have to decide which one to answer. And so it's a problem of making that decision. And this is known, philosophers have known of that problem in the name of Buridan's ass, where instead of the housewife having to decide whether to go to the front or the back door, you have a donkey who has to decide which of two bales of hay to go to, and he's equally distant from the two. And it was realized in the early 70s that computers act like this housewife or this donkey and have to make a choice between two different things. The way it happens in computers is that you have a clock that's inside the computer, and you have some event that's external to the computer. Maybe a message comes in or something. And the computer has to decide, it's doing one thing at a time, has to decide whether it should, since the clock pulse tells it to go to the next instruction or something, and the thing external interrupt says to stop what you're doing and do something else. And it turns out that if you don't design your circuits correctly, what can happen in that case is instead of saying either do A or do B, which in computer terms means either produce a 1 or a 0, it produces a 1/2. And computers are not very happy computer circuitry is not very happy when they see 1/2s, and it causes them to do weird things and to get different parts of the computer to do different things, and your computer crashes. And they discovered that, I think it was some DEC engineer who, there was a conference that was held on this, or a workshop that was held on this problem, and he mea culpa and said that a computer he designed would crash about every couple of weeks because of this problem. And it turns out this problem is, in a sense, unsolvable. What's unsolvable is that it's impossible to, if you're going to come out, you can come out with a 0 or a 1, but you can't do it in a bounded length of time. And which means the computer is screwed because it has to do it by the next clock cycle. And if you do it with a bounded length of time, you have a possibility of getting the 1/2. So what computers do, but you can build circuits that will almost always do it, pretty quickly. And matter of fact, that the probability of not having made the decision within a certain length of time decreases exponentially with the time. So in practice, you just wait a little while, and the chances of getting a 1/2 are negligible. So that's what computers do. They don't try to decide whether this event happened at the same time as the current clock pulse, but whether it happened before the clock pulse 3 times, 3 pulses later or something like that. And so engineers know about the problem, they design the circuits. That's not an issue. Engineers who don't know about the problem design circuits that will fail because of it. And I hope that these days all engineers know about the problem, but if an engineer doesn't know about the problem, he'll be able, or she will be able to solve it. They'll give you a circuit that they say solves it, and of course it doesn't. It just pushes the problem to a different part of the circuit. So that's the glitch or the arbiter problem. And when I wrote the bakery algorithm, someone at Compass pointed out this problem to me and said, well, your bakery algorithm doesn't require atomic operations, but it still requires solving this arbiter problem. And that's what got me interested in the arbiter. Should I go into the history of the papers and the publication and stuff, and non-publication, or not?
Well, I'm interested in what the impact was of the work that you did and that you published on the arbiter problem.
Okay. What I did is I told the problem to Dick Palais, who was my de facto thesis advisor at Brandeis and has become a friend. And he realized that an argument saying against the reason that people think that you should be able to solve the arbiter problem is that the argument that you can't is based on the fact that the real world is continuous. And people will argue, well, the real world isn't continuous because you can actually build this arbiter that goes 0 or 1. Well, it doesn't work. We don't know how to do it in bounded time, but it introduces discontinuity. And what Dick realized, that if you have the right definition of continuity, in fact, it is continuous. And theorems that tell you basically theorems that tell you that if a system is a solution to a certain kind of differential equation, then it is going to be continuous. And we believe that the world is described by these kinds of differential equations. They are continuous. That result applies, and therefore this is a mathematical proof of the impossibility of building an arbiter that works in a bounded length of time. So we wrote a paper on that. We sent it to some IEEE journal. Might have been Computer. No, not Computer. It might have been Transactions on Computers or something like that. At any rate, the engineers, this was all this mathematics, engineers knew nothing, had no idea what to do about that, and so they rejected the paper. I should mention that this arbiter problem has a long history of not recognized. And Charlie Mullner, who was a hardware engineer who worked on this problem, said he once submitted a paper on it, and the paper got rejected, and one reviewer wrote, "I'm an expert on this subject, and if this were a real problem, I would know about it, and since I don't know about it, it can't be a real problem, so the paper should be rejected." Literally, that's the story Charlie tells. So this paper was rejected from Transactions on Computers. I think by that time the engineers knew about the arbiter problem, but they still didn't know what to do with this paper. Later, a few years later, a similarly mathematical paper was actually published in Transactions on Computers, but the result wasn't as general as ours. I also wrote a paper called Buridan's Principle, which basically generalized that not just to computer type of issues, but to arbitrary real-world problems. For example, if you consider, suppose someone is driving up to a railroad crossing, one that just has flashing lights, and the lights start to flash. Well, he has to make the decision of whether to stop or whether to keep going in a bounded length of time, namely before the train gets there. And that's provably impossible. So in principle, it is possible for him it is impossible to avoid the possibility that he will be sitting on the railroad tracks when the train arrives. And I remember actually from my youth some train accident that happened where I think it was a school bus that for no apparent reason that went through a flashing light and was hit by the train in perfect visibility, and nobody could explain it. And it occurred to me that maybe that could be an explanation. I have no idea whether that kind of thing, which is in principle possible, whether it has a high enough probability of being a real problem. And that occurs, everywhere. And for example, you think of airline pilots have to make similar decisions, and they have to make them quickly, and could accidents actually occur? So I wrote a paper, and I wanted to get it to the more general scientific community. So I submitted it to Scientific American. No, I'm sorry, not Scientific. Oh, I forget. No, I think it was Science, the publication of the AAAS. And it was rejected. There were 4 reviews. They literally ranged from, this is a really important paper that should be published, to, surely this paper is a joke. And the 2 others were somewhat in the middle, less positive or negative. One was somewhat positive and one was somewhat negative, and 50% split was enough to get it rejected from Science. Usually when I get a paper rejected, if I think it deserved to be rejected, or there was a good argument for rejecting it, I will not try to publish again. But I felt that this was worth doing again, so I sent it to Nature, which is the British equivalent of Science. And I got back a letter from the editor who read the paper. He pointed out, well, I see this problem. And I realized it was a reasonable problem in the sense that for someone outside the audience that I'm familiar discussing with. So I described, the answer to his thing. And then he said, okay, and then he sent me something else and another issue. And I said, oh, yeah, that's a good point, but here's, the way, what it should have said to with that. And 2 or 3 exchanges like that. And I was never sure whether he was really serious or whether he just thought I was a crackpot and was humoring me. But after that exchange, I then got an email from some other editor saying that the original editor had been reassigned to something else, and your paper had been assigned to another editor, or to me, I guess, and I have this question. And he came back with basically, one of the questions that he had already, and at that point, I just let it drop. Finally, somebody, the paper was on my website, and somebody suggested I submit it to the Foundations of Physics journal, and I did, and that was accepted with no problem. But again, not the wide audience that I was hoping it would get.
So within computing, it sounds like this principle is probably not as widely understood as it should be still. Perhaps at the level of people who build circuits, it's understood, we hope. But perhaps not elsewhere, and these things arise in concurrent systems all the time, right?
The people who build computer hardware are aware of it. I don't know whether engineers who aren't principally computer hardware designers know about it. For example, back in the SIFT days, I tried to explain this problem to the people who were building the computers that were going to run SIFT, because SIFT had to worry about all possible sources of failures. And one possible source of failure was an arbitration failure. And I wanted to ask the engineers whether they understood this problem and what they could tell us about the probability of this happening. Well, in about 30 minutes, I was not able to explain the problem to those engineers so that they would understand it and realize that it was a real problem. Because they were, in those days, the avionics people, computers were just starting to be used in avionics, and the avionics people, knew an awful lot about, feedback control systems and such like that. Knew nothing about, computers or the digital domain. So the people who are building avionics hardware these days know about the arbiter problem and know how to take it into account. I don't know. I sure hope so.
Agreed. Did any other work come out of your interest in arbiter-free problems?
a couple of things. First of all, I mentioned Patronets, and I mentioned Mark graphs. Now, people in the small part of the hardware community that deal with asynchronous circuits and don't really understand things about arbiters and can try to build circuits without arbiters know that Mark graphs describe the kind of synchronization, or the kind of synchronization described by Mark graphs can be implemented without an arbiter. And it's significant because the kind of synchronization that Mark graphs represent seem to describe what I would call parallel computing as distinct from concurrent computing. Parallel computing, in my use of the terms, means a bunch of processors that are built deliberately to collaborate or joined together deliberately to work together on a single thing. Concurrency is where you have a bunch of processors sort of doing their own thing, but they involve some synchronization with others, and that in order to keep from stepping on each other's toes or bad things happening. And parallelism, when you read about big data computation, where you're using a server farm to compute, to process, all of the queries to Bing, in the last 24 hours, what you're doing is parallel computation. And there's software to do that. I've forgotten the names of the types. What's the MapReduce? So, for example, MapReduce is software that solves a kind of synchronization that is described by Mark graphs. At least that's what I presume MapReduce does. And for a long time, I thought that Mark graphs describe precisely the kind of synchronization that can be done without an arbiter. And so I decided to try to prove that and write a paper about it. Well, I discovered that I was wrong, that there actually is a weaker type of thing you can describe than, you can describe things that Mark graphs can't describe, but that can be done without an arbiter. And so I wrote a paper about that. And I wrote another paper that realized that parallel computing is important, even though I've generally stayed away from it as not being that interesting, because the problems of competition are much more difficult and interesting to solve than problems of cooperation. But I just realized that there was an algorithm that is sort of in the back of my mind, or that indicated how you could have an implementation of Mark graph synchronization by multiple processors that are communicating by shared memory. And so I wrote a paper about that, describing that algorithm. Mm-hmm. And that's, I think, the extent of what I've done in terms of arbiter problem.
And roughly when was that work?
I believe the work was done since I got to Microsoft, but I think it was done in the early part of
so a decade or so ago.
Yeah.
Yeah. Has this whole area of arbiter-free algorithms or implementations or whatever continued to receive a lot of attention, as far as you know?
I don't think it's ever received a lot of attention.
Okay.
There's a small community of hardware builders who are, well, almost all computers these days, or all computers you can go and buy in the store, work by having a clock. And they do something on each clock cycle. So they'll do something, wait for the gates to settle down, then go on to the next step, and that waiting is synchronized by a clock. This is a problem because your computers are so fast that propagating a clock signal from one end of a chip to another takes a significant amount of computing time, but engineers work hard to solve that problem. There's another small band of dedicated hardware builders. Ivan Sutherland is one of them, who believe that it's time to stop using clocks and to build asynchronous circuits. And so you want to avoid arbitration, whenever possible in building asynchronous circuits. And they have the advantage of potentially being much faster because if you're clocked, you have to go at the speed of the slowest component, or the worst case speed of the slowest component. Whereas if you're asynchronous, you can have things done as fast as the gates can actually do it. And I know I've heard Chuck Seitz, who's another member of that community, who I used to interact with, used to chat with him a bit, and I'm sure learned a fair amount from him. He has described building, basically really, really fast circuits for doing signal processing, with this asynchronous technique. But so far, it hasn't been adopted in the mainstream.
So it sounds like there's at least the potential you might do more work in this area in the future.
I think my days of working in that area are done, but somebody else might take it up.
Let's pick up the thread of your work in concurrency after that time. You continued to do work in concurrent algorithms, and I think there was a paper that you did not terribly long after that. Maybe it appeared around the same time as the Time and Clocks paper that was about concurrent garbage collection. Maybe the first paper, at least the first one I knew of, where you were working in some sense directly with Dijkstra, although I might have gotten that wrong. Can you talk about that a bit?
Oh, the genesis of my involvement, that Edskra Dijkstra wrote with some of the people around him, loosely call his disciples. The authors on the paper, I don't remember whether they were still students at that time or what, about a concurrent garbage collector. And he wrote it as an EWD report, a series of notes that Edskra distributed to fairly widely. And he sent me a copy, or I received a copy somehow. And I looked at the algorithm, and I realized that it could be simplified in a very simple way. Basically, it treated the free list as in a different way than it treated the rest of the data structure. And since it's a concurrent garbage collector, I realized that you could just treat it as just another part of the data structure, and moving something from the free list someplace else is the same as the basic problem as making any other change to the list structure. So I sent that suggestion, which to me seemed perfectly trivial, and Edskra thought that it was sufficiently novel and sufficiently interesting that he made me an author as a result of that. Something I imagine he regretted doing. There was an interesting story about that. Edgar wrote a proof of correctness of the algorithm, and it was in this prose-style, mathematical-style proof that people used and people still use to write proofs. And I got a letter from Edgar, those days when actually communicated by writing letters and sending them by post. And it said, it was a copy of the letter he sent to the editor withdrawing the paper that had been submitted, saying someone had found an error in it. Now, I found Dijkstra's proof very convincing, and I decided that, oh, there must have been just some minor insignificant error. And I had just developed the method of reasoning formally about concurrent algorithms that I published in, I think it was in the 77 paper proving the correctness of multiprocess programs. So I said, okay, I would sit down and write a correctness proof, and I'll discover the error that way, and I'm sure it'll be a trivial error, easy to fix. So I started writing a proof using this method that I had developed, and in about 15 minutes, I discovered the error. And it was a serious error. The algorithm was wrong. I had a hunch that it could be fixed by changing the order of two instructions. And I didn't understand why, I didn't know whether that would really work or have any very good idea of why, whether it would work or not. But I decided to give it a try, and of course, what I would do is use my method to write a proof. And it was hard work because writing a style of proof, you have to find an inductive invariant, which I won't go into now what that is, and that's hard, and especially at that time I had no practice in doing it. But I spent a weekend, and I was actually able to prove the correctness of my version of the algorithm. It turned out that Edgar had found a correction that involved changing the order of two different instructions. And because it was somewhat more efficient to do it that way, we used his and in rewriting the paper. But there I insisted that we give a more rigorous proof. And Edgar didn't want to give the really kind of detailed proof that I believe is necessary for making sure you don't have these little errors in algorithms. But we compromised, and we had the invariant, I believe, appeared in the paper, and not written formally, but written precisely. And so we had a sketch of that proof. And a little while later, David Grease, I think that he wrote that paper by himself, not with Susanowicki. But David Grease basically wrote his version of the exact kind of proof that I had written. It was at the same time I was developing my method. David Grease and his student Susanowicki, or I suppose since it was her thesis, it must have been Susanowicki and David Grease, were developing what was an equivalent method, logically equivalent, but it was more politically correct. Because remember that I told you that you needed to reason about the PC in order to write these kinds of proofs. But they didn't reason about the PC. They introduced they introduced auxiliary variables that would basically capture the difference. But there was another difference in the presentation, and in some sense, they were doing it in a the this method of reasoning about programs was introduced by Bob Floyd in a paper calling Assigning Meanings to Programs. So he did it in terms of writing, using flowcharts and annotating the flowcharts. Now, Tony Hoare developed another way of doing it called Hoare logic, in which it's, in some sense, it's a nicer way of doing things for sequential programs. And what Owicki and Grease did was present it in a language that made it look like they were using Hoare's method. But they weren't really using Hoare's method. They were using Floyd's method, but in disguise. And as a result, and their method and mine were logically equivalent. Their method became well known, and my method, it took about 10 years before people realized that what I was doing was really the same thing that they were doing. And but people were really confused by their method. And in fact, Edsger wrote an EWD calling my vision of the Owicki-Grease method, which he said was to explain it simply. And I thought that my reaction was, God, the poor people who tried to understand it based on his description. And when you look at it the way I did it, it's very obvious what's going on. You see it's clear that you're writing an invariant, and each step you're checking the invariant. But the global invariant was hidden in Owicki-Grease method. And, and these days, well, actually, I can't say whether people are still using the Owicki-Grease method. They don't write things in terms of flowchart. There was a paper by Ashcroft which preceded both my paper and the Owicki-Grease paper, in which he talked about doing things directly using the global invariant. And I thought that I was making an improvement on that by basically distributing the invariant as an annotation of the program, of the flowchart. And I've since realized that that's dumb. The correct way of doing it is just thinking directly in terms of state machines and essentially reasoning the same way Ed Ashcroft did. But in those days, I still thought doing things in terms of programming languages or things that look like programming languages was a good idea. I've since learned that if you're not writing a program, you shouldn't be using a programming language, and an algorithm isn't a program.
So that's a very interesting illustration of the tie-in between your work on algorithms, in particular concurrency algorithms, and the methods that you used, that you developed for proving the algorithms correct, which is, I think, another major thread in your work. And the two have been interwoven over, as far as I can tell, most of your career.
Yeah, well, in the early days, and there are lots of papers written about verified concurrent algorithms. What I think distinguished me from most of them was that I was doing this because I actually had algorithms to verify, and I needed things that worked in practice. And I looked at a lot of these things and say, I couldn't use that. So how, and even for the little things that I was going to use, and let alone try to scale them up to something bigger. David Grease and I think is, well, he has a long background, and I think the people who, I don't know whether he started as a mathematician or as an electrical engineer. I think he started as a mathematician, but the people from the old days, were in the US at any rate, somehow seemed to be more tied to real computing than people were, most people were, especially in Europe back in the 70s. And so, their method was, as I said, it's equivalent to mine, and in practical terms of whether you could use it made very little difference which one you were using.
I want to go back to something that you mentioned in passing in conjunction with the time clocks paper, which was the use of counters, which became an important notion in subsequent work. And in that time clocks paper, the counters are essentially unbounded. And that obviously had practical implications, which you explored further in some subsequent work about what you called registers. Could you tell us a little bit about that?
Well, as you mentioned, actually it's the bakery algorithm.
Sorry, bakery algorithm. Right, my mistake.
Where in the bakery algorithm, well, I sort of said it had no precedent. The precedent in it, which led to the name, was something that from my childhood, where we had a bakery in the neighborhood, and they had one of the little ticket servers that you took a ticket, and the next number, you waited for your number to be called. I suppose if I had grown up in a later era, it would have been the deli algorithm. And that's basically what the bakery algorithm does, except each process basically picks its own number based on numbers that other processors have. And it's possible for numbers to grow without bound if processors keep trying to enter the critical section. And so I realized that the algorithm required multiple registers to store a number, because you could run out of, you could overflow a single register, a 32-bit register, for example, in a fairly short time. So the reason why the fact that the registers didn't need, and the bakery algorithm didn't need to be atomic, meant that it was easy to implement them with multiple word registers, where only the reading of a single word was atomic. And so the first glance, it sounds like, oh, that solves the problem, because it doesn't matter what order you do reading and writing of the different words, it would still work. Except that if you weren't careful, you'd like to prove that the numbers, although not bounded, had some practical bound. For example, that the number would never be greater than the total number of times that somebody has been in its critical section. And it was not trivial to implement that. And so the paper I wrote, I think called On Concurrent Reading and Writing, gave algorithms for solving that problem. A nice statement of one of the problems solved in the algorithm was, suppose you have a clock in your computer, and the clock will count cyclically, say, for instance, 1 day or so. It might, cycle from 0 to 24 hours and then back to 0. But how do you accomplish that if your clock had to be multiple registers? And so the first question is, what does correctness mean? And correctness means that if the clock is counting the time, the value that a read returns is the value of time at some point during the interval in which it was reading. And so that's a nice problem, and if anybody hasn't seen the solution, I suggest it as a nice little exercise. So it was the bakery algorithm that led to me to look at that class of algorithms. There's a funny story that it turns out that you don't have to assume, if you have multiple words, that the reading and writing of an individual word is actually atomic. There's a weaker condition called regularity that I won't bother explaining, but it's weaker than atomicity. And it's a condition that if you give me, for a single bit, it's very easy to implement in hardware. As a matter of fact, the condition is basically trivial to satisfy for a single bit. And when I published the paper in CACM, I wanted to introduce the definition of a regular register and talk about how they could be used to implement this, for example, this kind of cyclical clock. But the editor said that the idea of reading a single bit non-atomically was just too mind-boggling, and that he didn't want to publish a paper with that. So I was forced to state that you had atomic bits, even though that wasn't a requirement. At any rate, that then eventually led me to think about, actually not eventually, but fairly quickly, thinking about what kind of registers do you have that are weaker than atomic register. And there's actually it's a weaker type than, and let me remember what the situation is. Oh, right. There are two classes of registers that are weaker than an atomic register. An atomic register is what you simply think of as, reading and writing happening as if they were instantaneous. One is called safe and the other is called regular. And the paper on concurrent reading and writing, it's safe registers are automatically regular, not automatically atomic. And safe registers are trivial to build. They're basically any way you might think of building a register would pretty much have to be out of multiple pieces. It would wind up having to be safe. Safe just means you get the right answer if you read it while nobody is writing it. So I consider the problem of implementing, first regular registers using safe registers, and then atomic registers using regular registers. Well, I was able to solve the first problem, not optimally, but at least solving it. And I believe that Gary Peterson later published a more efficient algorithm for doing that. And for going from regular registers to atomic registers, I was only able to solve it for two processors. That is a writer and a single reader. I proved the interesting result that you couldn't do it unless both processors were writing into something. By doing it, I meant with a bounded amount of storage. It's easy to do it if you have unbounded counters. Somewhat easy, but not in a bounded way. And so I was never able to figure out how to do it with multiple readers. And after I published my paper on it, there were a couple of papers published. One which claimed to have an algorithm that I have no idea why the authors believed that could possibly work. And then there were a couple of later algorithms that were really complicated. And I realized that the reason I never solved the problem is that the algorithms, the solutions, were sufficiently complicated that when things got that complicated, I just would give up. I don't know, sort of a combination of aesthetics and of not knowing if I had the mental power to deal with anything that complicated.
Was it your thought that this framework for different kinds of registers with varying degrees of complexity or utility, maybe I should say, was likely to lead to something else, or were you really focused on the problem that you had exposed in the bakery algorithm, which was that you do have these unbounded counters you have to deal with somehow?
Well, I said the problem of unbounded counters led me to think of what it means to build one counter out of one register out of bigger ones, out of smaller ones, and then that led me into considering these three classes of registers. And the safe register is one that I said that it's I know you can build them out of hardware. That's clear. And so that was the only register that I could say that physically I knew how to build. And again, this is I always regarded this as a physics problem.
Exactly.
And and actually when I started doing this stuff, it was fairly early, I think around 75 or so. And I gave a couple of talks about it, but nobody seemed interested in it. So I put it away, and I thought I had solved the problem of atomic registers. And then sometime much later, I think it was around 84, Jay Misra published a paper. I think it was Jay by himself. I don't think he published a lot of things with Mani Chandy, but I think that one was a paper by Jay himself, which started. It was heading in the direction of that work that I already did. So I decided, to write it up and publish it. And when I got back to writing it up, I suddenly realized that I couldn't imagine what kind of solution I had when I was talking about it in the 70s for the atomic register case, because I probably was able to look at my slides and what I seemed to have been saying was utter nonsense. But at any rate, so I sat down and came up with an algorithm. And fortunately, Fred Schneider was the editor of that paper. And he was an editor. He's incredible. I presume he doesn't do it edit anymore. But he actually, whenever every paper he published, he really read. And he went through the paper and he came to the proof of correctness of the atomicity paper. And he couldn't follow it. He said, I don't understand something or other. And I said, oh, Fred being thick, I'll go through it, and got on the phone to explain it to him, and it got to this point, and I said, by God, it didn't work. The proof was wrong, and in fact, the algorithm was wrong. And I've always been good at writing careful proofs, but it was before I had learned to write proofs the right way, hierarchically structured proofs. And so I realized the algorithm was incorrect, so I went back to the drawing board. And fortunately, there was an easy fix to the algorithm. And I wrote a much more careful proof, and that's what finally what got published. So I'm eternally grateful to Fred for saving me from the embarrassment of publishing an incorrect algorithm. Not completely, well, it was one that I did publish, but what happened is that it was I gave a talk at an invited lecture at one of the early PODCs, and then it was decided I should transcribe, I guess the recording was made. It was decided that I should transcribe the recording and turn it into and publish it in the next PODC proceedings, which I did. And in one of the slides, there was an algorithm that was nonsense, and I didn't pay attention to it when I was, I don't know how it got into my slides, but it would never have gotten into a paper if I had actually been writing it down, but I just reproduced the slides, and it was not a major part of the talk, but it was just a silly mistake or silly piece of nonsense that I'd written the slide without thinking about it. And but Fred saved me from what would have been the only, I think, really serious error in anything I've published. Although it was an interesting error that was actually in a footnote in the bakery algorithm. What I basically wrote without using the terminology, but in footnote, said that basically a single bit was automatically atomic. And I discovered when I started thinking about atomic registers that was wrong. It was not non-trivial even to get a single atomic bit.
The obvious is sometimes not so obvious.
Well, never believe that anything is obvious until you write a proof of it.
A good maxim. I want to pick up on a topic that you talked about a little bit earlier, but which became a major theme in your work on concurrency, really fault tolerance. And it goes back at least to the SIFT work that we were talking about earlier on. Byzantine agreement, which of course wasn't called Byzantine agreement or Byzantine faults early on, became a topic that was pretty significant in your work, and I'd like to.
Yeah, I suppose we should mention the story of why it did become the Byzantine general.
Yes, that would be a good thing to talk about.
Edgar Dijkstra published very early on in one of his papers. He posed a problem. It's called the dying philosopher's problem, and that's. A lot of people have used that as an example of how to do this in some language or other, and it received much more attention than I really thought it deserved. I mean, Edgar has did some brilliant work, and the Dying Philosophers was, didn't seem to be terribly important to me, but it got a lot more attention than things that really deserve more attention. And I realized it's because it had a cute story about it, involving philosophers eating bowls of spaghetti with required 2 forks, and each philosopher just had 1 fork or something like that. And so I realized, I thought that the problem was really important, and that it would be good to have a catchy story to go with it. Jim Gray had described a few
the Byzantine
years
agreement
earlier,
problem was very important.
That was the Byzantine agreement problem.
I just wanted to clarify.
Yeah, okay. And a couple of years earlier, I had heard from Jim Gray a description of what he described as the Chinese general's problem. And it's basically an impossibility result. It's quite important that I realized a lot later that Jim was probably the first one to state it and invented the Chinese general's story to go with it. So I decided the story of a bunch of generals who had to reach agreement on something, and they could only send messengers and stuff like that. And I originally called it the Albanian generals, because at that time Albania was the most communist country in the world, and it was a black hole. And I figured nobody in Albania is never going to object to that. Unfortunately, Jack Goldberg, who was my boss at SRI, said you really should think of something else, because there are Albanians in the world. And so I thought, and suddenly Byzantine generals, and of course with the connotation of intrigue, that was the perfect name. Mm-hmm. So that's how it got named. But you weren't originally talking about the name, you were talking about the problem. So what was your question?
Well, I think because this is such a fundamental thing, the transition from earlier work in which you assumed that things didn't fail to work in which failure had to be factored in and was in fact sort of almost fundamental, it seems to me an important transition. And obviously it's important to deal with failure. It becomes ever more important in the modern world. So I'd like to kind of hear how you got into that.
Well, that was obvious, because I had had the time clocks out paper with its algorithm for implementing an arbitrary state machine. But it was clear that when you had dealt with communication, you had to worry about messages being lost, and at the very least. So you had to worry about failures. And so that led me to say, how can I extend the algorithm from the time clocks paper and make it fault tolerant? And I guess when I was through, it didn't look much like the algorithm from the time clocks paper, but as I said, it was an obvious next step. And I wrote this paper, this forgotten paper in '77 about implementing an arbitrary state machine. And in the SIFT work, well, it didn't talk about, they didn't talk in terms of state machines. They had already abstracted the problem to sort of it's a kernel of just reaching agreement. And then to build a state machine, you just have a series of numbered agreements that on what the state machine should do next. But in the context of SIFT, SIFT was a synchronous system, so the system did something every 20 milliseconds or something. So there was a natural separation of an agreement protocol done every 20 milliseconds and ordered by time. So when you get to an asynchronous systems, you don't have that every 20 milliseconds, and so you use what's effectively a counter, and that somebody, to propose the next action of the state machine, you say, well, action 37 has been done, so now we're now agreeing on action 38.
And so that becomes the sequencing mechanism, and that Byzantine agreement is still the building block.
Yeah.
It's just that you don't have a real-time clock, you have a logical time clock.
Oh, well, but the other thing that's changed in the asynchronous world, at the same time there was this sort of shift of thinking, at least in my thinking, from the synchronous to the asynchronous world. There was also a shift in the failure model, in that people were worried about computers crashing, not about computers behaving erratically and doing the wrong thing. This can still be a problem in practice, but it's considered to be sufficiently rare that it can either be ignored, or you assume that you have some mechanism outside the system to stop the system and restart it again if that happens. I do remember once I think it was in either the 70s or early 80s, when the ARPANET, or I forget whether it was the ARPANET still or the internet, went down because some computer, didn't just crash, it started doing the wrong thing. And since the algorithms were presumably tolerant of, or people were worried about making them tolerant for crash failures, but not of Byzantine failure, but malicious failures that are called Byzantine failures, or even just failures causing computers to behave randomly. The ARPANET was not protected against that, and I don't know what they did to get it back up.
So this leads us, I think, to another project which became a whole series of works of yours around building reliable concurrent system, and that was Paxos. And you mentioned a little bit earlier that this was motivated by some work at CERC where you were trying to show how something couldn't work, and instead you got an algorithm out of it. Can you talk a little bit more about that, and then tell us a little bit about how that work came to the attention of the world outside CERC?
Oh, sure. First of all, before that, there was a book published by, it was a database book, but they had an algorithm supposed to deal with fault tolerance, and I looked at the algorithm and I said, that wasn't an algorithm to deal with fault tolerance, because they assumed that there was a leader, and if the system failed, well, you just get another leader. But that's a piece of magic.
Mm-hmm.
How do you select a leader and select a leader so that you never have two leaders at the same time? And what happens if you have? That's just as difficult as the problem that they claim to solve. So, I just ignored that, and which, in retrospect, was a mistake, because I think if I had thought about the problem and say not about just how their algorithm doesn't work, but I thought about how do I make that algorithm, how do I turn what they did into an algorithm that works, I think I would have gotten Paxos a couple of years earlier. But at any rate, as I said, the people at CERC were building the Echo file system, and I thought, and again, this was a case where we were just interested in crash failures. People believed that that's the way processors crashed almost all the time, and so you didn't have to worry about Byzantine failures, which was good because nobody knew at the time how to handle Byzantine failures except in the synchronous world, and it's not practical to build large synchronous systems these days, or I don't know, maybe possible these days, but it certainly wasn't the way things were going in the world today, really, in most of computing, because to build synchronous systems, you have to have systems that will respond to a message in a known bounded length of time. And the entire way computer communication has evolved, there's no way to put a bound on how long it's going to take a processor to respond to a message. As you know, if you use the net, and usually, the response comes back very quickly, but, it could take a minute to get a response. And so we couldn't assume any kind of synchrony, so it was an asynchronous system. And I thought that what they were trying to do in an asynchronous system was impossible. I guess maybe the reason I may have thought it, let me try to give a possible reason why I thought it was impossible, and there's an interesting backstory to that. When I was interviewing at Park back in '85, I gave a talk, and I must have described some of the Byzantine generals' work. And I made the statement that in order to get the fault tolerance, or to solve the problem that I was trying to solve, you needed to use real time, because in the absence of real time, there's no way to distinguish between a process that has failed or a process that is just acting slowly. And I knew I was trying to slip something under the rug, which I do in lectures, because there's a fixed amount of time, and sometimes I have to ignore embarrassing things, not because I want to hide them, but just because I want to get through the lecture. But at any rate, Butler Lampson caught me on that, and he said, well, it's true what you say, that you can't distinguish between whether something was failed or just acting slowly, but that doesn't mean that you couldn't write an algorithm that worked without really knowing whether a process had failed or not, but just does the right thing if there aren't too many failures or whatever. And of course, I couldn't answer it on the spot. I went back home later and thought about the problem, and I came up with some argument that it was impossible. And unfortunately, that email has been lost, and I don't remember what it was. But I realized that, it wasn't rigorous. I mean, certainly what I was writing wasn't rigorous enough. And it just wasn't very satisfying, and I never carried it any further. But I just had this feeling, that there was some result there. And some number of years later, and I don't remember when it was published, that there was the famous Fisher-Lynch-Patterson result, known as the FLP result, which essentially proved that what I was saying was impossible was in fact impossible. And it was a fantastic, beautiful paper, and what they said was much simpler and much more general than anything I was envisioning. So, that was one of the most, if not the most important papers on distributed systems that he ever written. But at any rate, that experience may have made me thought that what the echo people were trying to do was impossible. Although I think it was that the FLP paper came later, but I'm not positive about that. At any rate, so I sat down to try to prove that it couldn't be done. And instead of coming up with a proof, I came up with an algorithm. I would sort of say, well, an algorithm to do this has to do this, so that can't work because of something. Well, actually, this could work because of that something, but you do something else, and that follow and suddenly say, whoops, there's an algorithm here. But it's interesting, the relation with the FLP result. The FLP result says that in an asynchronous system, you can't build something that guarantees that consistency in reaching consensus. That is, where you're never going to get two different processes that'll disagree on what value was chosen. But it says you can't guarantee that a value eventually will be chosen. And people have shown that this is an explanation, post facto explanation, not something that goes through my mind at the time. But it's been shown that there are random solutions to the problem, which don't guarantee, but guarantee with high probability that that is, as time goes on, as the algorithm advances, the probability that you won't have reached a decision gets smaller and smaller. And so what I would say that Paxos does is it's an algorithm that guarantees consistency, and it gets termination if you're lucky, and it sort of gives engineering hints as to what you do so that you have a good probability of being lucky, and sort of reduces the problem to one of being lucky, which has engineering solutions. But even if you're not lucky, you're not going to lose consistency. And that's what the Paxos algorithm does. And that's what I came up with. The problem with the paper was, having been successful with a story with the Byzantine generals, I decided to write a story for the Paxos paper. And it was about, the reason it's called the Paxos paper is the storyline is this paper is written by an archaeologist of this ancient civilization of Paxos, and they had this parliament, and this is how they built the parliament. And I had a lot of fun with it. The paper was called The Part-Time Parliament. And sort of examples of that's the part of the story or how it would be used, is I would have the story, and it gave the names of the characters Greek names, or more precisely, their actual names transliterated into Greek. I had Leo Gibas's help in doing that. He did the I had to add a few non-existent symbols to the Greek language to get some phonemes that weren't in Greek. But and I thought that people would be able to know people who do any kind of mathematics should know enough Greek letters to be able to know, what an alpha and a beta looks like. And so, come reasonably close to, if not figuring out the names, at least be able to keep, to read them in their head so they'll be able to understand the story. But apparently that was beyond the capacity of most of the readers. And so that part, confused them. And I submitted the paper to TOX, I believe, Transactions on Computer Systems. And the referees came back and said, well, this is interesting, not a very important paper, but it would be worth publishing if you got rid of all of that Greek stuff. And I was just annoyed about the lack of humor, the referees, and I just let it drop. Fortunately, and almost nobody understood what the paper was about, except for Butler Lampson. And he understood its significance, is that this gives you a way of implementing, and in a fairly practical way, any system, or any a kernel of a system, the part that really required that keeps the system working as a unison, rather than keeps the processors from going off in their own way and getting chaos. And you can use Paxos as the kernel of any distributed system. And he went around giving lectures about it. Also, in the at roughly the same time, Barbara Liskov and a student of hers, Brian Oakey, were working on a distributed file system, I think. And they had buried inside of their distributed file system something they called time-stamped replication, which essentially was the same as the Paxos algorithm. And at some point I heard Butler say that, time-stamped replication is the same as Paxos, and I looked at the paper that they had published, and I saw nothing in there that looked like Paxos. So, I dutifully would, when I wrote about Paxos, would say, quote Butler as saying that, this algorithm is also devised by Liskov and Oakey, without really believing it. And then years later, Mike Burrows said, oh, don't read the papers, read Brian's thesis. And I looked in Brian's thesis, and there indeed was very clearly the same algorithm. But I don't feel guilty about it being called Paxos rather than time-stamped replication, because they never published a proof. And as far as I'm concerned, an algorithm without a proof is a conjecture. I think Barbara has come to realize that, and I should mention that she and her student Miguel Castro, well, it was Miguel Castro's thesis, actually solved the problem of Byzantine agreement, asynchronous Byzantine agreement, or Byzantine agreement in an asynchronous system. And there they had a very careful proof of correctness. And so they essentially have what's Byzantized version of Paxos.
So you mentioned that the editors and the reviewers were not particularly
Oh,
kind
right.
to the paper.
Yes.
What happened to it?
Well, one thing, I thought it was really a terrible paper. And at some point, when a system was being built at CERC, and Ed Lee, he was the, okay. And I think it was Ed Lee who was told by somebody that, oh, you should read this paper about Paxos because that's what they need. And he read it and he had no trouble with it. So I feel not so much that, less guilty about it and, willing to put more of the responsibility on the reviewers and the readers. But at any rate, it was clearly an important paper, and it was finally published in around 91, I think. And what happened is that, Ken Berman. Ken Berman was had become the editor of Tox, and he was about to leave his editorship. And he said, gee, it's about time that Paxos paper were published. So he said, I'll publish it, but you just update it to talk about what's been done in the meantime. And I didn't really feel like doing that. So what I did is I got Keith Marzullo to do that part for me and to carry on the story. Being an archaeologist, it was that this manuscript was found in the back offices of Tox, and the author was away on an archaeological expedition and could not be reached, and so Keith wrote this, I forget what it's called, some explanation, which was put in, in separate text as his contribution. So he did the annotations, and it was published.
So I think if I got my chronology right, the work on Echo was in the late 80s that inspired you to work on Paxos, and the first shot at submitting the Paxos paper was in the early 90s, and the paper didn't actually appear until the late 90s. Is that right?
Oh, that's right. It's the late 90s that the paper appeared. We need to check the date on that. I don't remember the publication date of Paxos, but I recall it being approximately 10 years after it was submitted.
Yes, that's early 90s and late 90s.
Yeah.
What struck me in mind there. And so the sort of core idea in Paxos then turned out to have rather long legs in terms of the work that you did subsequently, of applying the idea again in different situations with different constraints that led to different solutions. Can you talk about sort of that space of papers? You mentioned some of them earlier, or at least in general, disk Paxos and
Yep.
fast Paxos and so on.
Okay, the next one was, as I mentioned, disk Paxos. And when we were writing the paper, Ellie sort of said, well, it's really exactly the same as Paxos. And I started writing the paper that tried to make disk Paxos look like just a variant of Paxos. And in fact, Butler Lamson has written a paper called The ABCDs of Paxos, who claims that he has one germ of an algorithm from which he derives both ordinary Paxos, disk Paxos, and Byzantine Paxos, the Liskov-Castro algorithm. But I've looked at the paper. I haven't tried to look at it in great detail, but I'm really skeptical, because my experience with the disk Paxos is that if you looked at it high level, it seemed that way, but when you try to work out the details, it didn't work. And there was just one basic difference in the two algorithms, so they really are separate algorithms, and there's no Ur algorithm that they can both be derived from. Since that time, there was another thing that happened, that algorithm called cheap Paxos, and that happened because a Microsoft engineer, I had moved to Microsoft at that time, needed an algorithm that, for tolerate a single failure, you need, with ordinary Paxos, you need 3 processors. But most of the time, 2 processors are enough. And the third processor you can sort of think of it as a backup, but in particular, it doesn't need to keep up with the other 2 processors until there's a failure, in which case it has to take over from one of the 2 processors. So I believe it's Mike Massa was the engineer, Microsoft engineer. He had an idea for using an asymmetric protocol that most of the time just used those 2 processors, and then they would have either some weak processor, or just if you're a third processor, have some other computer that's busy doing other things but can come back in when needed. And he had a vague idea of how to do it, and I came up with the actual, the precise algorithm and wrote the proof, and that's how that paper came. Since then, I did some other work with Li Dong Zhao and Dalia Malkley about having to do with reconfiguration. One of the problems in fault tolerance is, say, for Paxos, you need 3 processors to tolerate 1 fault. Well, 1 processor dies, you need to replace it. Now, if it's really just 3 processors, then you bring in a new computer and just call it by the same name as the old one, and it keeps going. But sometimes you really want to move things to different computers. So you want to do some kind of what's called reconfiguration, where you change the processors that are actually running the system. And Paxos, or in the state machine approach, there's a very simple way of doing that. You let part of the machine state be the set of processors that are choosing the commands. Well, you have a chicken and egg problem if you do it the naive way, because you have to know what the current state is to choose what the next command is, but how do you know what the current state is? And so so what was proposed in the original Paxos paper was, I said that the Paxons did it by making the state at time t, that the processors who choose, or the legislators who choose the command at time t, be the ones according to the state at time t-3, or command number t-3. Well, 3 was a totally arbitrary number, and I figured that everybody would realize it's a totally arbitrary number. But a lot of people kept saying, what's 3? Why did he choose 3? And something. At any rate, there were, so at any rate, we did a few improvements, optimizations, or whether it's about how to do reconfiguration. And Dalia said that this method of putting it into the state isn't going to fly with engineers because they don't understand it. And so we worked out a different procedure, which was actually a variant of cheap Paxos. But I don't think much of that work has had a significant impact. I think it's the basic Paxos algorithm that's the one that's still used.
So say a little bit about the impact that it's had. Obviously, it got used by people who were, in your immediate vicinity because they learned about it quickly. But with the difficulty of the word getting out through this hard to read paper and so on, how did Paxos become, shall we say, a standard thing in building large-scale distributed systems?
I really don't know what happened. I'm sure Butler had a large effect in going around and telling people about it. I know it's at the point where an Amazon engineer said to me, there are two ways to build a reliable distributed system. One, you can start with Paxos, or two, you can build a system that isn't really reliable.
So they obviously believe, or he did. Are there other companies that you know of that have adopted it?
Oh, sure. Google, they're, I think they call it the Chubby Locks or something like that. It uses Paxos. I think there are I've been told that there are at least 3 implementations of Paxos in Microsoft systems. It has become, it has become standard. There are other algorithms that are in use that I don't know about. There's an algorithm called Raft, which is really simple, that the creators of Raft claim that one of its advantage over Paxos is its simplicity. I take that with a grain of salt. I heard somebody recently give a lecture on Raft, and it didn't seem too simple to me, but I think that what's going on is they're measuring simplicity by you show it to something and people say, whether or not they say they understand it. And to me, simplicity means you show it to people and they can prove it's correct, then prove it's correct. And somebody else had told me is that Raft is basically an optimization of Paxos. And there's plenty of room for optimizations in Paxos. Paxos is it's a fundamental algorithm, and there are lots of optimizations you can make to it. And there's something else called Zookeeper, but I don't know what its relation to Paxos is.
And at least some of this is in the open source world these days, right?
Yeah, I'm sure there are open source implementations of Paxos since the patent, I believe, has expired.
We'll talk about patents a little bit later, maybe.